All right, let's talk more about neural networks. My name is Rituddin, and today we are talking about gradient descent. This will be mostly based on 3 Blue 1 Brown's video about gradient descent, so I'll be linking that down below. I'll be using many of his diagrams and pictures from his video as well, so his due credit will be down in the description. All right, so let's start off with a recap. Starting off, we take the example of handwritten digit recognition. They're rendered on a 28 by 28 pixel grid, which is where we get this. Let me just turn on the laser pointer real quick. Which is where we get our 784 inputs from. So this outputs into 10 numbers. So 1 through 10. That's what we have as our output, and then we have a bunch of parameters as well, which is what we call the weights and the biases. So here's the software recognizing handwritten digits and then converting them into what number it thinks it is. And then weights and biases are basically what help a neural network learn. Weights determine how much influence each input has on the next layer. So these layers right here, the first layer, second, third, and fourth layers. And then it's kind of like adjusting the volume on different audio channels, basically. Biases act like a baseline adjustment, ensuring that neurons can activate even when inputs are low or zero. During training, the network fine tunes these values to recognize patterns and make better predictions. So basically, how 3 blue, 1 brown put it, we're hoping that the first layer could take in these handwritten digits, and then maybe the second layer can notice some patterns in them, some lines or something, and then maybe the third layer could recognize certain like loops and whatnot, and then the fourth layer could piece all those all the information from the previous layers and then put them all together to basically understand what number the handwritten digit is. All right, let's move on to the next slide. Cost functions. So to get the cost function, we basically take in all the inputs available from the parameters, so the 13,002 weights and biases that we have available, and then we basically output one number, which is the cost. And the cost basically goes up if the model is less accurate, or if it's like doing a bad job. And then it has a lower cost function or lower cost if the model is doing a good job and if it's very accurate. So there's many parameters. It's based on the training examples, but let's talk more about how we get this how we like tell the program or the model to improve itself, because just telling the model that it's doing a bad job doesn't exactly help it. Like, sure, it's doing a bad job, but what can it do to improve itself? That's where we take this into example. So to get an improved cost function, or improved cost rather, we can look for a local minimum. Um, so we can get the local minimum here, the local minimum here, for example, or there's a global minimum here as well. So getting a global minimum is particularly hard because you may not necessarily know where the global minimum is. But getting a local minimum, it's a bit more feasible. So for the extent of this, it's more feasible to go for a local minimum and go from there. It's because it'll be probably mostly accurate for most use cases by then, and if it needs to go for the global minimum, then it'll take additional resources for that to happen. So let's just do this. Okay, so basically how we get to a local minimum is we just choose a like a random point to start. So let's say we start like here, for example, and we just go down, we end up here, right? So let me just erase. All right. So we end up right here. So how we determine which way to go and how to navigate is based on a slope. So let's say our slope goes like this. We want, if a slope is going negative, we want to go down, obviously, because we're looking for a local minimum. So we'll just keep nudging down and down until we end up here, where we'll get more of a flat slope, and then we'll eventually realize that this is a local minimum. So there's nowhere else to go. We found a local minimum, and then that's a way to it is basically as accurate as it gets for now. And then let's say we start out somewhere else. So like let me just erase everything. All right. Let's say we start out here, for example, and our slope is a positive one. We want to slowly nudge over this way towards the as the slope is going down. So we keep going down. Let's say the ball is right here. The slope is more like this right now. And we start here. The slope is more flat because we're reaching close to the local minimum. And as we get closer to the local minimum, the slope is flatter and our model is basically improving itself. Now let's talk a bit more in depth about gradient descent. Alright, so this picture on the left, given to us by 3 Blue 1 Brown's video, shows basically what we saw in the previous slide in a slightly different field of play. So we basically, to get the gradient descent, we compute the gradient direction, and then, we just take a small step downhill from the gradient, and then we repeat. That's essentially what gradient descent is. So we calculate for the gradient direction, and then we just go the opposite of it, and then just take a small step, and then we calculate it again, then take another small step, and then we just keep repeating that process. So like I said, gradient descent is just essentially just the process of nudging a variable, or nudging a input rather, multiplied by a certain amount of the negative gradient until we get to the local minimum of the cost function. On the right side, we have a column vector that basically helps us visualize our problem at hand easier. Because as you know, we have over 13,000 inputs, and that is quite hard to visualize. At least for me, it is. So with the help of a column vector like this, we could see which values affect our gradient descent the most. So we can see which values matter more than others. So basically, they have their own weights to them. So focusing on certain jumps would matter way more than some other jumps. So like, for example, we see that some of these just increases somewhat, just a little, or decreases a lot, or increases the gradient descent a lot. So from here, we can see which ones matter more, and then which ones matter less, and then we can put priority on them as well. Let's analyze the network a bit now. So basically how the model that 3 Blue 1 Brown has been showing off in his video, and that I've been also talking about so far, guesses it's like the numbers, the handwritten digits, is based on not what we've technically said it's based off of. So earlier I said like the different layers of the neurons could be one layer could be like for like loops, another layer could be like for certain lines. But in reality, that's not actually what they look for. As we can see on the right hand side, it says what the second layer of the neurons actually look for. It just looks like a mess to us because we don't have the same type of learning that this is going through. So to us, it shows that it's not really looking for these loops and patterns that a human would look for. So why was this taught this in the first place? And the explanation to this is basically that this isn't really an endpoint, as 3 Blue 1 Brown stated. This is a starting point for where more advanced topics would take place. And then we'd progress this model until it's able to do basically what we're looking for. At its current stage, this is a very outdated model that's just trained on the basics only. And then on the left hand side, it shows that even if we were to give the model like a very garbage picture, so like the one on the let me get my laser pointer. So right here, for example, we can just see this is obviously not a handwritten digit. This is just like random pixels. But even if we were to give this random assortment of pixels to the model, it would just confidently assume that this is the number 5. So why can it confidently do this? Because as far as the model is concerned, it has to be confident in these in its actions based on the cost function. So since it has a relatively low cost function, it has to be confident in its answers because its accuracy at this point of the video is like 96% plus. And while that can be improved and it is relatively decent right now, that is not the point of what we're trying to get across. The model was not trained with certain things in mind, and it's based on a lot of constraints. So at its current state, it's very limited and based on old um, methodology that's not really particularly too relevant nowadays, other than just being the foundation. Um, and then after we build upon these foundations, these basics, we can move on to more advanced topics, and then we can continue to improve this model uh, using it as our baseline rather than our endpoint. But that's basically it for me. Please go watch 3 Blue 1 Brown's video that I'll link down in the description, and I'll catch you guys later.